See, triatomic is a non-linear shape. Anyway, here if you are considering this translational degrees of freedom, it can move along x-axis, y-axis and z-axis. So, therefore, total independent terms, number of independent terms is 3 here. For rotational degrees of freedom, suppose if you are considering this is the x-axis, this is the y-axis, this is the z-axis, as any line which is along one axis, but moment of inertia is corresponding to another one. Therefore, we can exist Ix, Iy and Jz. So, therefore, total number of degrees of freedom here 3 here total. Therefore, total number of degrees of freedom is equal to 6. Monoatomic, once again I am writing the chart of this degrees of freedom. Monoatomic 3 here, diatomic I am considering only the room temperature first, is a 3 plus 2 5, and triatomic here 6. The monoatomic, it will possess only the translational one, whereas the diatomic translation plus rotational, but one along the one axis that will be 0. Here what happens that it will possess the translation 3 and rotation also 3. These are at room temperature. See, how can we apply these degrees of freedom for gases? We are going to discuss now. Next one. Last class, we explained the specific heat. What do you mean by specific heat here? S is equal 1 by m here, dq by dt. So, the amount of heat supplied to the system for unit mass for raising its temperature by 1 unity. For gases, what we are taking this, instead of this mass, we are taking that number of moles dq by dt here. So, here we can consider as in the place of m, we are considering n. This is the per unit mass here, this is number of moles. This is the amount of heat supplied to the gas for raising its temperature by unity for 1 mole. For gases, there are the specific heats. This one we are calling as molar specific heat. For gases, there are the two specific heats. One is constant pressure and constant volume. So, your heat supplying to the gas at this constant pressure, that is what we are calling as Cp. Here the heat supplied to the gas at constant volume, we are taking that constant dq by dt here. Here, if you from this equipartition of energy, next one, energy here, let the gas contains degrees of freedom is F. For each degree of freedom for 1 mole of the gas, it will contains that energy is equal 1 by 2 RT per mole or 1 by 2 KT per molecule. So, this is equipartition of energy. Let it gas contains F degrees of freedom. For each degrees of freedom, for 1 mole of the gas, it will consist, what is that, 1 by 2 RT. For 1 molecule, what should get that? 1 by 2 KT here. Let it contains F number of degrees of freedom. Just we are seeing this last class, last section, monoatomic gas 3 here, diatomic room temperature is 3 plus 2 5 and triatomic 3 plus 3 6. See F number of freedom. Suppose if it is a 3 here, 3 into 1 by 2 RT, and suppose if it is considering for the molecule 3 into 1 by 2 KT. See here, if let generalization F number of degrees of freedom, so total energy is equal, what is that, F into 1 by 2 KT. If you are writing this Cp or Cv here, first we are taking the Cv is equal 1 by n dq by dt here. This is the energy. So, dq is equal energy E is equal Q. This can be equal to what is that? F into 1 by 2 RT. Whereas I am taking dq by dt per 1 mole. This is per 1 mole I am saying this. So 1 by n dq by dt here. So we can take this dq by dt. How can we write down? F into 1 by 2 R. See, per 1 mole we can write down what we can take this F by 2 R. This is molar specific heat at constant volume. We are taking in terms of degrees of freedom F by 2 R. Next one, Cp. We know the relation between the Cp and Cv. Cp minus Cv is equal to R. So Cp is equal to Cv plus R. Then Cp is equal, Cv is equal, what is that? F by 2 R plus R. This we can write down F by 2 plus 1 into R. Then we are taking another constant, that is gamma. This can be equal to Cb by Cv. This one will be F by 2 plus 1 into R by F by 2 into R. R gets cancelled. Gamma is equal F plus 2 by F. Again this is divided by 2 and this is also divided by 2. That gets cancelled. Gamma is equal 1 plus 2 by F. So here this one is an adiabatic constant. We are going to discuss that tomorrow, the laws of thermodynamics here. See, 1 plus 2 by 3. If we are taken this F value for different atomic gases like this, suppose if it is a monoatomic gas, so how many number of the degrees of freedom? Only 3. So Cv is equal, what we got this? F by 2 R. So we can write down in the number of degrees of freedom F is equal to 3 by 2 R. What about the Cp here? F by 2 plus 1 into R. So this can be 3 by 2 plus 1 into R. So this will be 3 plus 2 5 by 2 here. So gamma is equal Cp by Cv. So this can be, what should be that? 5R by 2 by 3R by 2. This can be 5 by 3. Suppose if they are asking Cv, Cp, you can find out the Cp value, Cv value by using these formulas. Suppose if they are asking the directly gamma value here, directly you can use 1 plus 2 by F. So F is equal, what is that? 3 here. We can directly take 2 by 3 here, 3 plus 2 here, 5 by 3. Directly you will get the gamma value by using this equation. Similarly, for diatomic gases. See, at room temperature, number of degrees of freedom is 5, 3 plus 2, 3 for translational, 2 for rotational. Cv is equal, same, what is that? F by 2 R. So this can be, what is that? F by 2, 5 by 2 R here. And Cp is equal F by 2 plus 1 into R. So this can be 5 by 2 plus 1, 7 by 2 R here. And gamma value is equal Cp by Cv here. This can be 7 by 5, or we can cross check with 1 plus 2 by F. This can be 1 plus 2 by 5. This will be 7 by 5. For triatomic, so for the degrees of freedom at this translational is 3 and rotational is also 3. I am taking the room temperature. So total will be 6. So your Cv value will be F by 2 R here, and substituting total will be 6. This will be 3R, and Cp value F by 2 plus 1 into R. This can be, so 6 by 2 here, 3 plus 1 into R, 4R. Gamma is equal Cp by Cv here. This can be 4 by 3, or we can check this 1 plus 2 by F. So 1 plus 2 by 6 value here, 6 plus 2, 8 by 6, this can be 4 by 3. This is about how we are relating this Cp and Cv with degrees of freedom. Suppose if they are asking that common values of this, suppose this is a mixture, let this gas 1 is present and gas 2 is present, it will have some Cp value, we cannot know this is a monatomic or diatomic, it will have some other Cp value. So, Cp1 I am taking, this other two gas Cp2, this is a completely mixture, so combined, and it is a non-reacting mixture, one gas cannot react with other, it is a Cv1, and this for the same one gas Cv1 here, for the same two gas the Cv value is Cv2 here, for this gamma 1 and gamma 2. So, tomorrow we will start this how the two gases can be combined in the one mixture. See different common constant pressure here, this is different molar specific volumes here and different gamma 1 gamma 2. How can we take this mixture of this gamma, mixture of this R1 gamma 1 and gamma 2. So, next one after that, so tomorrow again we are focus on laws of thermodynamics. New syllabus, first we are starting with first law of thermodynamics, then application of first law of thermodynamics, and next one other one is cyclic process. After that non-cyclic process. Next one, how the work done by the gases during different process. We are going to discuss in the tomorrow in the chapter is what is the laws of thermodynamics, how this what is meant by cyclic process, non-cyclic process and work done by the gases in different process. We are going to discuss this. See, today you practice what we discussed about that gamma values, what about the Cp values and Cv values, you practice the problems. So, what about this gamma, what about that Cv, what about the Cv, already we discussed about the relation between them, that one